In this video, we're going to start to look at the energetics of an enzyme reaction. Right. So to understand the energetics of a reaction, it's good to think about transition states, or what's called transition state theory. So let's think of a reaction. We have HA bonded to HB plus HC. In our reaction is to break the covalent bond between HA and HB and form a covalent bond between HB and HC. That means that some part during our reaction, you're going to have HA bonded to HB bonded to HC. We call this a transition state. It's halfway between where we started and to where we're going to. We call this also our highest energy form. And if we look at the energy of this reaction, you can see that we have a giant bump when we go to this HA, HB, HC complex. The energy from our reactants to the top of this transition state is called the free energy of activation, and we call this delta G double dagger. And this is our slowest step of the reaction. So it's the rate determining step, where the rate of our reaction equals exponent raised to the power of negative delta G double dagger divided by RT. So that's the free energy of activation, while the free energy of the reaction is simply reactants and products, that gap. So don't get those two confused. From reactants top of the hill is free energy of activation. Reactants to product is the delta G of the reaction. Now, normally chemical reactions are multi-steps. So here we have an intermediate being formed that we're going to call I. And if that happens, we have two transition steps. So if A goes to I goes to P, so our first reaction is A going to our first transition state, A double dagger. Then we go down to I. I goes to our second transition state, I double dagger. And finally, we go down to P. So you see I is an intermediate because it's actually low in energy. So you're going to have some of I build up before you go to P. Now, based on which transition is higher energy, that transition will be your rate determining step. So if we look at the red line from A to A double dagger is small compared to I double dagger. So here the red line is showing that the second step is rate determining. While in the blue line, the distance from A to A double dagger is bigger than from I to I double dagger. So A is now the rate determining step in the blue line. And if we look at the reaction of catalyzed versus uncatalyzed, so here if we look at this plot, the blue is uncatalyzed and the red is catalyzed, you see there is a gap from this double dagger state. The difference we call delta G double dagger. The change in free energy of transition state. So that's what the delta G means. It's the difference in delta G double dagger. Confusing, I know, but it's just change in. So how fast a catalyst goes compared to the uncatalyzed reaction, we call that rate enhancement, and its exponent delta G or delta G double dagger divided by RT. So that is this gap in how fast a catalyst speeds up things. Now a catalyst will catalyze both the forward and the reverse reaction. So it will go forward faster and reverse faster. But notice that for the products and the reactants, the lines merge. So it doesn't matter if you're if you're catalyzed or not, the delta G of the reaction does not change. So the free energy, the amount of products and reactants in a catalyzed and uncatalyzed reaction remains the same. All that happens is that you speed up your slowest step, so you speed up the entire reaction. And that's it for this video. I will see you in the next video.